So, ladies and gentlemen, someone also identified an issue with the video. I've got to make sure or sort of check out what's causing that. Someone said the video audio is out of sync with the slides, and I've got to figure out why that is. So appreciate you flagging this to my attention. Okay, so I've asked you to watch some videos in preparation for this class and the last one. What were those videos on? Delays. Good. Delays are part of the building blocks of system dynamics models, and they're perhaps the most common higher level structure beyond the level of stock in isolation or flow in isolation that we see in system dynamics. So we talk about first order delays and second order delays. And today I asked you to look at information on I think higher order delays and aging chains, and last time for first order delay. But I want to review this material. Maybe we could do some interactive exercises. So tell me, when I say a first order delay, what do I mean? What's a delayed version of what? Beautiful. Beautiful. That's right. That's exactly right. So, that's the answer that I was hoping for. And it's fantastic. Now, it turns out that in a first order delay, the outflow, how does the current value of the outflow? How do we measure a flow? It's in terms of what? If a stock has units X, let's say people, what's the units or the dimensions at least associated with the outflow? It's sorry? Yes, it's X per time. Good, that's right. So we have this. We have some X per time, and that flow, that rate of flow, is proportional in a first order delay to what? It's proportional to the proportion. I mean, it's just some constant multiplied times the value of the stock. Good. Oh, great. You folks you inspire me. Now, it'd be nice if I heard it in a Greek chorus, all together, could speak in unison. But hearing even one person makes me feel good. At least someone watched the video. Okay. You know, I have my ways of tracking. Well, okay, I can't track whether particular people, but I can track the numbers. Okay, so tell me what to draw. If I want to draw a first order delay, tell me what to draw. Suppose I'm interested in a first order delay that also involves some sort of inflow. So there's, because we're talking about outflow, proportional inflow. So what do I draw? How many stocks? One. Good, one stock. Okay. Hey, let's do this. Oh man, let's do this interactively. You folks have a machine in front of you. You can work along. Okay, so let's go create a new model and let's draw it. So what do I need to draw? I need to draw. Oh, I need to plug the machine in, or it won't be drawing anything. So this must be dead. Oh man, they still haven't wired up the room either, I guess. Oh man, look at that. Okay. Okay, so let's go here. Any logic? There we go. Okay. Incidentally, this is Vensim, which is another popular system dynamics package, which in previous years I've covered, but for Unity and sort of covering things, this year we're sticking purely with AnyLogic. And I'll try to make this full screen here. Okay. So we're going to be going through several different examples, but I'm going to do them in this package, AnyLogic. So here's AnyLogic. So I want to create a new model, right? And let's go do that here. Okay, things are taking a bit of time. Okay, new, and we're going to call it first order delays. Okay? Yeah? If you don't have a computer in front of you and you want to work with someone, I'd encourage you to pull over to someone nearby you. First order delays. There we go. Creating first order delay model here. And let's close some of these windows. I don't need to be in debug mode. There we go. Okay. So we're going to go to the main canvas. And we're going to go down and add in a stock. So here's a stock. And I will call it X, capital X. Okay, what else do I need for first order delay? Okay, inflow and outflow. Good. So let's go add inflows and outflows. Okay. So this will be called inflow, and this will be called outflow, right? Okay. Okay, great. Now, the inflow here, I'm just going to right now make it a simple quantity, okay? I'm going to make it the value 1. Okay, constant 1. Boom. What does that mean? It means one person per what? Per time unit. And what is the time unit? Where can I find that in any logic model? Yeah, it's for the model as a whole, and I want to make it years. Okay? So I go to the model as a whole, and I want to make it years. These will be useful skills for projects that you're going to be doing, for assignments. I'm going to be posting the first assignment today, and it'll be useful to know where to go to set the units. Okay? Okay. Great. So I made this inflow 1, and I'm going to, what else do I need to specify? When I specify a stock, what do I need to specify for it? The initial value. I'm just going to leave the initial value as 0. Okay, ladies and gentlemen, what further thing do I need to add to complete this as a first order delay? Okay, the outflow depends how on the stock. It depends in a, begins with L, linear way. It's proportional to the stock. In other words, it's some constant times the value of the stock. Where that constant, if it's times the value of the stock, that constant represents a chance per unit time, per year in this case, of leaving. So ladies and gentlemen, suppose I want to set this up so that people have who are in the stock have a 10% chance per year of leaving the stock. How would I do that? What do I have to add? Speak in unison. What do I need to add? I need to add okay, I'm going to add a parameter. It's a constant in any case. I'm going to add a constant, and this will be probability per year of departure. Okay, I'm just being very verbose about it, but that's our chance per year. It's not a probability. It's a probability per year. A probability would have to be between what? It could be no less than 0 and no more than 1. This can be no less than 0 to be sure, but it can be greater than 1. What would that mean if it's greater than 1? Students also get confused about this. What would it mean if it's greater than 1, a probability per year? We'll come to that. We'll come to that. We'll be covering that in a minute, the intuitions here. There's a very simple intuition. But just be aware, this is not a probability. It's a probability per year. That's examinable material. It's a probability density. How many people here are physics or engineering physics? Okay, one stalwart soul. That's great. And you will have encountered these before. Basically, when you're dealing with continuous time that plays out in a continuous way rather than a staggered way, then you're dealing with probability densities, chance per unit time. Okay? At any point, they could flow out. It's a chance per year that they'll flow out. The greater it is, the more quickly they'll flow out on average. Okay, probability per year aperture. Okay? Okay, so ladies and gentlemen, that's a constant, and we're going to make that constant, we're going to specify default value for it of 0.1. 10% chance per year. Good. Ladies and gentlemen, what do I need to complete a first order delay? Okay, so I hear a link. From whence does this link come and whither does it go? It comes from where? From the parameter, and it goes to where? To outflow. Good. Okay, good. And does that complete the picture? That's a great start, but there's one more link needed. And from whence does that link arise? From the stock, and whither does it go? To the outflow. Okay, good. Excellent. Okay. So that's good. And we just have one final piece to specify. What do we still have to specify? What still lies before us to specify? The outflow. How does the outflow depend? Remember, ladies and gentlemen, in system dynamics, you do not specify formulas for the stocks. The stocks, the dynamics of the stocks, the change in stocks over time is dictated by the what? By the flows. For what do you specify formulas? For the flows, and for any variables that are just convenient names for formulas. We call auxiliary variables, or dynamic variables here. So we have to specify formulas for the flows. Those formulas over time will dictate the rates of the flow, and that is going to determine how the value of the stock evolves. For a stock, we only specify one thing, and that's the initial value. Thank you. Values for the flows, they depend on the values of the stock right now, at this point in time. And then how that stock changes, that'll depend on the values of the flows, how it changes over the next little bit of time. Okay, so ladies and gentlemen, what's the formula for outflow? Okay, good. Yeah. So if you have a 10% chance per year, and you have 1,000 people in X, the number of people on average who leave per year is 0.1 times 1,000, which is 100. Does that make sense to people? Okay. Okay. So probability times X. On average, 100 people leave per year if 1,000 people are at risk, right? Okay. That's great. And maybe, we'll, just to make these kind of more humanly understandable, let's make that inflow 1,000 instead of 1. Just so it's more easily thought of as people per unit time. 1,000 people per year. Okay? People come through that, the stock's still starting at 0. So ladies and gentlemen, what should I see? So we heard earlier by our guest from engineering that the outflow is a delayed version of the inflow. So what will we see as the outflow from the stock? What should we see? Okay, so it's starting at 0, and we'll avail ourselves of this board for this preliminary guess. Starting at 0, and it's going to go up. That's right. How will it go up? In what way will it go up? Will it go up faster and faster and faster? Will it go up in a straight line? Will it go up slower and slower over time in a convex way? Okay, it'll go up slower until it reaches what asymptote? Until it reaches what? It approaches what value? Well, okay, in this case, we changed the inflow to be 1,000, so up till 1,000. It'll be approaching 1,000. Good. So let's verify that intuition, and then let's reason why. Okay. So let's run this. Okay, so we're going to run this first order delay in terms of simulation, and here I am, and here we're going to go look at this, and we're going to watch the value of this flow, and the prognostications were accurate. Oh, look at that. No, it's not going up to 1,000 for the value of the stock. It's going up to a value of 1,000 for the value of the what? The value of the flow is going up to 1,000. The flow is a delayed the outflow is a delayed version of the inflow. Not perfectly delayed. If we're perfectly delayed at time 0, the inflow was 1,000, and this would have just been a delayed version, just offset. But instead, it goes up in a gradual way. Was ist das? Why is this? What is this? What is it? What's going on that makes it this behavior? Why is it that you see it kind of go up slower and slower? Okay, yeah. So initially, lots and lots of people come in, but there's almost no one leaving because there's very few people here, right? So there's very few people leaving initially. Watch this reasoning. This will be very helpful the next 2 lectures, okay? So just bear with it. In this case, I know it's a very simple example, but the basic reasoning will suit you well for much more complex examples. So this is why I call these the building blocks. And if you understand these building blocks, you can start to see how the behavior of larger patterns play out. Okay, so initially, X is rising very, very quickly because lots of people are coming in, 1,000 people per year, and almost no one is leaving because there's very few people here, right? Very few people are leaving, lots are coming in, so it goes up quickly. And then over time, as this value rises, there's more and more people leaving. More and more people are going out. And it's going up until the point where it's going up as long as what? X will be rising as long as what? Inflow is greater than outflow. So X is going to be rising. And let me put that again. Let's make it crystal clear. X is rising as long as inflow is greater than outflow. And as X rises, what else rises? The outflow, right? The outflow is going to rise. And as a result, X will be rising, but it will be rising slower, right? Because there's more and more outflow now. X will continue to rise, though, as long as the inflow is greater than the outflow, but it will rise slower and slower, because each little bit it goes up, there's more outflow. And it's going to rise till what situation? It's going to rise until the inflow equals outflow. Outflow is equal to the inflow. And there you see it, ladies and gentlemen. And you heard it from back first. The outflow equals the inflow. The outflow is a delayed version of the inflow. The value of this stock at equilibrium is what? 10,000. Why? Where does that come from? Give me a formula for that. Inflow times alpha. Or inflow divided by alpha in this case. If alpha is this, depending how you define alpha, yeah. If alpha is this probability here, it's inflow 1,000 divided by 0.1. Why? Well, it's at that level of the stock that what will be the case? Out equals in. Because if the stock is the inflow divided by this thing, and if the outflow is the value of the stock, inflow divided by this thing, times this thing, you get the outflow equals the inflow, right? Okay. You people grok that? Grok or not? Grok. Okay, good. Thank you. You grok. Okay, so here we have a first order delay illustrated, and we see that the inflow is greater than the outflow. Let's now enrich the situation a bit, and we're going to, in a Bachish fashion, we're going to do a fugue on this. Okay, but it will be not a fugue, not not musical in nature, but mathematical. Okay? So, ladies and gentlemen, let us compute. So, let's riff on this theme. First of all, I want you to tell me right now another way that I could define this first-order delay that's mathematically identical, but it's phrased in quantities that sometimes are more readily available than the chance per year of departure. Give me another way of specifying this. Aha, mean time until exit. So, right now, we have a formula here that is the value of the stock times this probability per year per departure. So if there are 1,000 people at risk and there's a 10% chance per year of leaving, then 100 people per year on average leave, right? It's about the outflow. Ladies and gentlemen, let's convert that now to a situation where we have a mean time in that stock of a certain value. So I'm going to, I can do this in several different ways. I'm going to define a value that's called mean time in stock, okay? Commonly we call it mean residence time, but I'll be a little bit pedantic about it to make it clear in this case. Mean time in stock. Can anyone give me a formula? Well, okay, give me a formula for what outflow would be in terms of mean time in stock. We'll take this guy, we'll temporarily disconnect it, and we will come back and revisit it. Tell me what the formula would be if we wanted to formulate the outflow in terms of mean time in the stock. What would that formula be? Okay, X divided by mean time. Good. Good. X divided by the mean time in stock. Oops. X divided by mean time in stock. Boom. Okay. And then, guess what, folks? What is mean time in stock going to depend on? On what will it depend? It'll depend on the probability per year of departure. Give me a formula for mean time in stock in terms of the probability per year of departure. Sorry? Yes, the reciprocal of it. 1 divided by probability per year of departure. So let's be very clear about this because they are mathematically identical. And if you don't see that, let's just spend a little bit of time with it. The formula in one case is the outflow. We'll call this probability per year of departure alpha. The probability, the formula for the outflow in one case is alpha times X, right? Alpha X, right? 10% per year times the value of the stock is 1,000 people at risk, 10% per year leave. The average number of leave per year is 100 per year. 0.1 times that, right? Okay, the other formulation, though, is in terms of a tau, a variable tau. And here the outflow, this is mean time in stock, whereas alpha was probability per year of leaving stock, okay? If we formulate in terms of the outflow in terms of mean time in the stock, what's the formula? Ellen gave it earlier. X divided by tau. Good. Oops. I don't know why that came up that way. Good. Okay. And what is tau in terms of alpha? Tau is simply, it's 1 over alpha. I mean, folks, X divided by tau is X divided by 1 over alpha, which is just alpha times X. You see, it's one and the same. It's completely identical mathematically. Whether you call it this, 1 over alpha, and you divide by it, you divide by 1 over alpha, or you multiply by alpha, they're the same thing. The mean time in the stock is the same as 1 over the probability per year of leaving the stock. We just often know one rather than the other. It's convenient to specify, it's convenient to think of it in terms of one rather than the other, and we use that. But they're two identical formulations. Do you folks grok that? Okay, good. Good. So we could specify it alternatively this way. And if you do so, using this dynamic variable, which is a good thing to know about for your assignments, for example, you can go run this, and you will see that this is dynamic variable. By the way, it would change it even if this changed, and you will see it behaving in an identical fashion. This will go up to 10,000 on average, and this will go up to something proportional to that, but which actually reflects the value of the inflow. It goes up until those are equal. And it's at that point that it's achieved stasis. Remember, well, I should ask you, ladies and gentlemen, formulate for me this question, because if you don't do it now, you may on the final exam. What feedback is present in this formulation? Is it a positive feedback or a negative feedback? Is it a reinforcing or balancing loop? Balancing loop. And if were I a bit taller, I could look it in the eye. Right? We have the loop here. X increases the outflow. What's the polarity of this link? What's the polarity of this link? X to outflow. Is the polarity plus or minus? X to outflow. Right. If X increases, the more people at risk. If we have 10 people at risk rather than 0, will the outflow increase or decrease? It will increase. Goes up with the number. So this is a plus link. How about the link from this back to this? If we have greater outflow, does X decrease or increase? Decreases. So it's a plus link here and a minus link here, going back this other way. So it's just drawn on that. That's our negative feedback. You folks see that? Okay. Okay. Good. We've talked about the equilibrium value of that stock. The equilibrium value can be formulated as either the inflow divided by alpha or the inflow multiplied by tau, right? This is the mean time. So they spend on average 10 years there. The number of people in that stock will be the value of the inflow times 10. Those from epidemiology background will recognize this. If you have an infection out there, you have an incidence rate and a prevalence, unfortunately sometimes called prevalence rate, and it's in equilibrium, the prevalence is going to equal the number of years you stay with the infection times the annual incidence. Okay? Okay, good, good. I'm glad you folks see that. So that was some basic understanding with stocks and flows. This is stuff that you have to be very confident about going forward. We're going to see these same basic relationships in agent-based modeling. This is not going away. This is not a system dynamic thing. It's a thing about how processes in the world operate, and we'll use some of the same reasoning with system dynamics, okay? Obviously, with agent-based modeling. So this is not just a thing to remember for this lecture, not just for this module of the course, for this type of modeling. It's for the entire course. Any questions to ask about this? Yes, question. Sure. You mean, in other words, the formulas used for them? Sure. The formulas that I used for the parameter was just, I gave it a default value of 0.1. And for the dynamic variable thing from here, I gave it a formula of 1 divided by the probability per year of departure. This mean time in stock, what did I call this up here? I called it tau. That's just tau. That mean time in stock is just tau. So it's 1 divided by the probability per year of departure. It's 1 over alpha. Is that helpful? Question?
I thought that it's parameter, but it's not mean time in stock. It's not parameter.
No, it's a dynamic variable. Yeah. So a dynamic variable allows you to find one quantity in terms of another, and those quantities may be changing. So it automatically recomputes it. It's quite nifty. It's like a cell in Excel. If the things it depends on change, it automatically updates its value accordingly, instantly. So it does a calculation through. So this thing happens to depend just on that right now, which is constant. So it's a constant. But in general, it may be changing. And these are very useful quantities. We'll be using them quite a bit, probably starting next time. Okay? Good. Ladies and gentlemen, other questions on this? Yes? Why is the stock? The initial value of the stock is 0 because we chose it to start empty. But it doesn't stay 0. It rises rapidly at first. We could start it, I chose it to start 0 to have it be a dramatic effect where it's really far off, but it's obvious that it's how it changes as a result. I didn't want it to start in equilibrium, although that would be another possibility. So it was just a choice for this example. But in general, we describe the initial value as kind of the start, the value we believe best obtains at the start of the simulation, or the one that we want to use to kind of think through things. Okay? So other questions? Great questions. I really welcome these questions. This is why I ask you to watch videos, so we can have these questions to address the issues. Okay? Okay, ladies and gentlemen, let's do something more with this. Let's go run this thing, and I want to ask you this. So we're going to run this, and here we're going to watch this, and we're going to see this thing change. Okay? Fair enough. Ladies and gentlemen, what would happen if I went here and, we can't click on it, darn it. Okay, we're going to have to change it. Let's go create a parameter that will be called inflow rate. Okay? We're going to go set a parameter called inflow rate. And this will be something we can change. And we're going to give it a value of 1,000. And we will set the inflow to be equal to the inflow rate. This is just because we can't explicitly change it while it's running for the inflow. Okay? There we go. So we'll set inflow to be equal to inflow rate. There we go. Did people see how I did that? I added a parameter, I made its value 1,000, and then I set inflow to equal inflow rate. People comfortable with that? Who would like me to show you anything with that? Okay? Let us compute. Okay? Okay. So, ladies and gentlemen, we're going to run this model, and you should see the same behavior elicited earlier. You should see the stock undergoes some dynamics and so on in just the same sort of way. It's mathematical, we haven't changed anything, right? We just put it into a parameter rather than putting in the flow. But now, ladies and gentlemen, by virtue of having done that, we can click this parameter and we can edit its value. And you're going to tell me what's going to happen. Okay? I'd like to think this through, ladies and gentlemen. Okay, so here's the value of the stock. It's rising rapidly and then going more slowly as more and more people start leaving and so on. Okay, ladies and gentlemen, suppose I change this value from 1,000 to 500. What will happen? What will happen when I change it from 1,000 to 500? What will decrease by half? Okay, immediately? Or they'll start quickly and then go towards a new equilibrium. Okay, there we go. Okay, it's going down. That's not the most effective way to look at it, is it? But it's going down quickly at first, and then it's going towards a new equilibrium, which will be 5,000, 500 divided by 0.1, or 500 times 10, 500 times 10, or 500 divided by 0.1, right? People comfortable with that? I want you to be rock solid on this, okay? Okay, so now we're going to this new equilibrium. Great. This is a first order delay. It followed the change in the input, although with a certain delay. I can change the input, it will follow it. It'll go quickly at first and then slower. So suppose I were to move this down, move this back to 1,000. I click this little edit button here, right? And I change it back to 1,000. What will happen? Sorry? Yeah. It'll rise very quickly at first. It's rocketing up, and then it will rise slower, right? So again, a delayed version. People grok that. Okay. Okay. I want these solid intuitions because we're going to depend on them for the next couple lectures, okay? Okay. So, ladies and gentlemen, now let's do something different. It's approaching our equilibrium value of 10,000, where what equals what? At the equilibrium for first order delay, what equals what? Inflow equals outflow. Thank you. Okay. So, ladies and gentlemen, now I want to do something different. I want to change the value of the stock to a different value. I want to perturb the value of the stock. I want to change it to go from approximately 10,000 to 5,000. What will happen? Okay. So I want to change the stock from a value of 10,000 to 5,000. What will happen? The outflow will decrease because we've lowered the value of the stock. The outflow is going to depend on some constant time set, so the outflow will decrease, right? Sorry, I shouldn't be referring to this thing. The outflow is equal to some constant times the value of the stock. So if we halve the value of the stock, the outflow will here be halved. Okay, so I'm changing it to 500, and let's go back into graph mode here. And there we see it decreased, and then what's happening? It's bouncing back. This is a regulatory loop. It has a negative feedback. It wants to bring the system back into balance. If this stock goes down to 5,000, it will be out of balance. Out of balance in what sense, ladies and gentlemen? Inflow no longer equals outflow. The inflow will be rushing in at a much faster rate than the outflow is rushing out. Right? Your bathtub drain is going to be plugged up, because the value of the stock times this probability per year is going to be much smaller than the inflow. It's going to be half the value of the inflow. So water will be rising in the tub to bring it back into equilibrium. It resists change. You push on it, you change its value, you perturb it, and it bounces back. And it seeks back its equilibrium. People appreciate that. Want that intuition. Okay? Okay. Good. Now, ladies and gentlemen, formulate for me an alternative way to specify this first order delay with one flow. Single flow. Remember, flows don't have to always be positive. Flows can be negative. Flow into a stock can sometimes be negative. So could someone give me a single flow version of this? Let's build it. Let's build it alongside this one. So we're going to build a separate one, and it's going to be called X2. Okay, we'll call it X2, and there will be just a single flow into this. Okay, this is going to be inflow. Okay, inflow 2. Sorry, inflow 2. But I'm actually going to call it not inflow, excuse me. That invites misunderstanding. Ladies and gentlemen, particularly those from computer science background, naming is important. How you name things is key for your understanding later and the understanding of other people who see the model. It's not a matter to be taken lightly. These are small toy examples, so I don't sweat it that much. But in a real model, we sweat it a lot. It matters. It has gravity to it as a decision. There's dangers if you don't name things properly that people misunderstand and make mistakes. In this case, I'll call it net flow. Okay, net flow. Or net inflow. Better yet, net inflow. Okay? Okay, notice the top one has inflow, this bottom one is net inflow. Okay? So I'm just putting that there. Okay. Ladies and gentlemen, I'll move them closer just so you can see that. Ladies and gentlemen. Oop. Okay. Ladies and gentlemen, I would like you now to tell me how would I formulate a value of a formula for net flow that's equivalent to the formula up top, or that's equivalent to the situation up top. This is important about viewing this in a regulatory fashion, this particular example. So give me a formula by which I could formulate this, which would be all in a single formula, the same as the top one. Well, we're going to start unpacking these things in a mathematical sense. And what better way to do it than now? What better time to start than now? Can anyone give me a formula, a state equation formula, a differential equation that would describe, thank you very much for closing that, that would specify the change in x over time, the rate of change in x. We write the rate of change in x per unit time as x dot, with a nod to one of the two inventors of the calculus. I believe Newton preferred dx dt, while his German counterpart preferred x dot. Okay, so can anyone give me a formula? The rate of change of x, it's equal to what? Okay, well, there's going to be, okay, okay. We could specify, okay, it's going to equal inflow minus outflow. After all, if it was just inflow, the rate of change of x, how quickly would it go up? It will be the rate of inflow, right? 10 people per year, x dot, the rate of change of x, people per year, 10. If it were 200 coming in per year, the rate of change of x, if it were only inflow, would be 200. So it's inflow, and how does it relate to outflow? Minus outflow. Okay, this is what I'm unpacking here. We're going to depend on quite a bit. So I want you to understand the rate of change of x, right? In Leibnizian location equals inflow minus outflow. Okay? Okay. What is inflow? Give me the rate. Give me the rate for inflow in mathematical terms. It's a formula. We've specified it up. Inflow is just inflow rate in this case. It's just this thing called inflow rate. Okay? Inflow rate. And what is outflow? Okay, alpha x. Or we could have written it as x over tau, right? Okay, there we go. This is a differential equation. This is a constant. In this case, it's 1,000, right? 1,000 minus alpha x. That's a differential equation. And it turns out it has a solution. Now, in general, very simple differential equations we can figure out analytically. We can actually solve them in so-called enclosed form. We can write down a formula for how it would be solved. And this is an example of that class of equation. And, ladies and gentlemen, if we were to solve this, it would involve doing variable substitution, and it would involve dividing the x, you put the x over on this side, and you have an alpha here, you integrate both sides, and over on the left-hand side, you'd get so you have dt on the right, and you have dx over x on the left, and you integrate both, and it's ln of x equals alpha t, and you take the exponent of both sides, and you get x, and what will come out of it once you go through the variable substitution is x at time t equals, so there's going to be a term here that's going to be the value of the inflow rate, divided by alpha, okay, that's going to be sort of a long-term value, and then given its initial value, it's going to be 1 minus e to the minus alpha t. This is e to the minus alpha t. Okay, so at time 0, x of t is going to be 0, because 1 minus e to the 0 is 1 minus 1, so this is going to be 0. And over time, as t becomes larger and larger, 1 minus e to the alpha t will approach 1, and it will approach this. So if you draw that out, it will approach this. I'm not asking you to know how to solve this as a differential equation, but you should be aware that a simple case like this, we can actually solve. We can write down a formula. If I gave that to those who here from engineering background, like myself, and we could sit down, we could solve it. Those from physics background, well, they'd probably eat it before breakfast and feel very full as a result. Okay, so the point is, a simple system like this we could solve. Next time, we'll be getting into cases where we can't solve it. We don't know how to solve it. It's nonlinear, and things go wonky. We cannot write down a formula. And the only way we can solve it, ladies and gentlemen, is by running a simulation, the topic that occupies us for this semester. So, in this case, we can write down a solution. But this solution, the steps to this solution, suggest a way we could have a single flow. What would this single net flow be in terms of inflow and outflow? It would simply be this net flow. Sometimes it'll be positive, sometimes it'll be negative. And what will its value be in terms of inflow and outflow? The value of the net flow will simply be, inflow minus outflow. Good. So we could reformulate this using a single flow as inflow minus outflow. And that would work perfectly well. But we want this thing to be self-contained. We don't want it here to depend on this thing above there. So we're going to formulate it in a slightly different way, okay? This is how we're going to formulate it, ladies and gentlemen. And I want you to watch through the underlying mathematics of this, okay? Okay. So what we're going to do here is we're going to have this depend, well, before we add a link, we're going to add something here to dynamic variable called target. Okay? Target. It's going to be going after a target. It's going to be changing x2 to approach a target. And we're going to formulate a thing here. I want you to know how to do this because it's an important other perspective on first order delays. We're going to say it's totally mathematically identical to the top, but net inflow now is going to be equal to something that involves target, involves net inflow here, involves x2 here, and it's moreover going to be dependent on something that is going to depend on this probability per year of departure or this mean time. We could have it depend on either one here. I'm going to just clean this up a little bit by pulling this down, pulling this down. So we'll have this kind of right nearby, and we will have this net inflow depend on this probability per year of departure. Okay, there we go. And I'm gonna, sorry, I'm plan the spatial layout a little bit better here. Oh gosh, there we go. And this is not being that pretty, but that will do, I guess. Come on, there we are. Okay, so we have a probability per year of departure, and I'm going to drag this guy around so it's clear for labeling that variable. Okay, so this guy will still depend on it, but so will net inflow. Okay, now watch this, ladies and gentlemen. The net inflow here, this is the key formula. This is the formula I want you to know, to remember. The key formula here will be this. It will be, so the idea here, folks, so you're going to help me derive what the key formula is. I'm going to ask you. Okay, so the idea, folks, is we're going to want to increase x2 if target is bigger than x2. If the thing we're shooting for is above x2, we want to raise x2. That means we want the net inflow to be what? To be positive or negative. If we want to raise x2, the net inflow is positive. If the target is less than x2, we want to lower x2. So we want the net inflow to be negative. The higher the discrepancy, if target is way above x2, we want x2 to rise quickly. If target is way below x2, we want it to rise, to go down quickly. If target is just a bit above x2, we want it to rise, but more slowly. Ladies and gentlemen, can anyone give me the basics of a formula, a term that should be in this formula, such that those things would be the case? How would we make it go up if target is greater than x2? Give me it's a really simple formula that would just put aside the issue of how quickly it goes up, but just give me a formula such that it will go up, the net inflow will be positive if target is greater than x2. Try and develop your intuitions, because you may be asked this in the final exam. So give me a formula. What would it involve? It involves target and involves x2. It's about the simplest formula you can imagine that would allow this property to be the case. If target is greater than x2, the value will be positive. Good, excellent. Target minus x2. Okay, that's the key bit. It's the discrepancy. If target is way above x2, it'll go up faster. If target is way below x2, it'll go. If this is far less than this, then this minus that will be negative, and it'll go down very quickly. If target is just a bit above x2, it'll go up. This will be a small difference. x2 will go up, it'll go up slow. That's the basic properties. And we're almost there, ladies and gentlemen. We're almost there. What we need to do is we need to now specify one final component, which is how quickly it changes. And it turns out how quickly it changes is given by none other than, guess what? Can anyone see? Just think ahead, those of you who are feeling a bit bored. Think ahead. For this to be mathematically equivalent to this, what does x2 need to be multiplied by? Probability per year of departure. Remember, this outflow here is x times probability per year of departure. We can view it like that, right? Alpha x, right? So we need a probability per year of departure. That's kind of our adjustment time, how quickly we adjust if target is off base. If target's bigger, this is how this reflects how quickly you adjust. Another way we could specify it would be what, ladies and gentlemen? Would be divided by what? Mean time in stock. This kind of gives the mean adjustment time for getting X2 in line with target. If target is off, we're going to rush to adjust X2 to track target. We're just about done. We're just about done. Just about done making these two equivalent. So here we have this thing, it's like we're following a target. The target goes up, we go up. Target goes down, we go down. We're following. It's a feedback control system. For those whom that's a meaningful concept. So here, X2 is being adjusted by the discrepancy here. Ultimately, what value will X2 hold? Riddle me this. Ultimately, what value will X2 hold? At what net inflow will X2 be constant? At what net inflow will X2 be held constant? At net flow? Okay, yeah, at X2 equal, well, okay. So at what value of the inflow will X2 be constant? At the net inflow of what? 0. And that will be achieved when what equals what? Target equals X2. So when X2 reaches target, it won't need to change anymore, right? Do people understand that? Okay. Okay. So folks, if we want this guy to be equivalent to that guy, and we know that that occurs when that equilibrium in the top one occurs when X equals what? Inflow rate times tau, or inflow rate divided by alpha? Guess what target needs to be totally equivalent to this? It needs to be inflow rate and then, what do you think? I'm tempted to do it in terms of mean time in stock, but we'll do it with this. We'll do it with probability per year. So I'm going to, well, you know, it would be nice to have it in terms of that probability of that mean time in stock. I think it's a little bit easier to slip through. So I'm going to rearrange these some more. Come on, get down there. Let's just bring this over there. It's just a layout issue. And let's have this guy now depend not on probability per year. Let's have him depend on mean time in stock. And then let's have target depend on inflow rate and mean time in stock too. Okay. So ladies and gentlemen, that is the target at which this thing is going. The value for target here, this formula here, come on. This formula is equal to, the value for target is equal to what? Is anyone following this? The value for target is, yeah, X2 will be in stasis. It will be in balance when it equals target. Therefore, by the situation up here, that occurs when what? X is equal to inflow rate, X is equal to inflow rate times this mean time. So here we just have the target is equal to the inflow rate times the mean time. Okay? Ladies and gentlemen, we have now formulated, and you should be able to run this model here. Let's just specify this. This guy depends on mean time in stock here. So I have reformulated this model. This model was specified in this way. Let me just make this very mathematically clear. It was specified the rate of change, people per unit time. Positive, it's going up. Negative, it's going down. In the original formulation, what we had is this thing equals inflow rate, okay? That's the inflow minus the outflow. So you always have. When you formulate this, you're going to need to feel comfortable doing this. If you have a stock and flow model, how do you turn it into a differential equation? You read out each of the flows in turn, and you write down the formula for them. And on the left-hand side is the derivative of the state variable, the change in this per unit time. People are comfortable with that. This is 10. X dot is 10, it means it's going up by 10 people per year. X dot is minus 10, it means it's going down by 10 people per year. People okay with that? Okay. X dot equals the inflow minus the outflow. That's the general thing. If there are many inflows, it would be the sum of the inflows minus the sum of the outflows. Okay. Inflow rate minus, and up here we have X divided by tau. Right? Where tau is just 1 over the probability. So it's equivalent to X times alpha, alpha times X. That's the top formulation. People okay with that? So let me put that's this guy here. Like that. Right? Let's do the bottom one now. I hear a few Greek choruses, and it unsettles me. Chori. The bottom one. X dot. What is the formula I used for it? Well, now we have just one net flow. There's just going to be one term here. And what is the net flow? By the way, this is X2, right? I could have called this X2 just to make it clear that we're talking about the bottom one, right? Talk about this guy here. Okay. But I'll call it X just to make it clear. It's equivalent. What do I have at the bottom? What's the formula here? It's target, right? Target, minus what? X divided by tau, or let's put it over tau here. Right? And guess what this is, folks? What is the value of target? Target is inflow rate. Remember, target is the target towards which this goes, at which will be in equilibrium. X2 will be in equilibrium when the inflow rate divided by, or times tau is when the value of the stock. This will be in equilibrium. The top one will be in equilibrium when the value of the stock is inflow rate times tau, right? And to target, it's inflow rate times tau. And so here we go. We have inflow rate. I'm just expanding target here. Just writing this formula again. But inflow rate times tau minus X. All I did is expanded target divided by tau. And what does that turn into, folks? It's the same. It just cancels, right? This equals, so when I was a graduate student, there was another graduate student who we sort of viewed as the god of TAs. He was like superb TA. And every day before his lecture, he would plan out exactly where on each board he would be writing each thing. So he'd know exactly what order to put things in and what columns to put them in, so that by the end of an hour and a half or what have you, everything had just the space allotted to it. And my service as a teacher is all too mortal. So I'm sorry I had to move this alpha, okay? This thing is equal to inflow rate equal inflow rate minus X over tau, which is none other than what? This guy. These two are equivalent, folks. So this one here. These guys here are just another way of writing this one above, and that's what's described here by this kind of bottom one. It includes this mean time in stock and probably per year. So these are two ways of writing a first order delay. We could think of it as the stock is heading towards a target and adjusting to meet the target, where the target is equal to the target is equal to the inflow rate times or what was the inflow rate up here times tau. But normally we think of it as a target. We think of it as tracking something. So maybe target is based on some level of risk, and you have a perceived risk, and it takes some time to update your sense of risk. And so here, target would be the risk out there in the population, and the mean time in stock would be the mean time you would keep kind of your perception. In the meantime, to change your perception of this external risk. Maybe target represents a amount of air pollution in one region, and the mean time represents how quickly that air pollution spreads to another region. In any case, we could formulate first order delays using this target, where target is some thing at which we're aiming in this stock. So we adjust the stock to match target. Okay? Two different ways of formulating it. They're each useful for their intuitions. And generally, if we use the bottom one, we don't deal with an inflow rate. We're just dealing with some target. Some target that the stock is going to go to over time. And we write the formulas in exactly this sort of way. Target minus X over some tau, where tau is the adjustment constant. How quickly we adjust our perceptions, adjust the situation in terms of our stock, how quickly our stock adjusts. Does that make sense? So formulate a first order delay in terms of following, you could think of it as, and this is important. I don't think I've ever made this point before in this class, and it is an examinable point, and I mean any previous version of this class. So the first of these really views the first order delay as dictating the flow being a delayed version of the outflow being a delayed version of the inflow. You heard it earlier. The outflow in this first one can be viewed as a delayed version of inflow, right? People comfortable with that? We saw that earlier, right? It goes up and follows it. The bottom one, the stock follows the target as a delayed version of the target. If the target goes up, the stock is sure to follow. Like the little lamb and Mary. Right? So target goes down, the stock follows. It's a delayed version of target. Very useful as a modeling approach to have that flexibility because, again, we want to characterize things about like how quickly people's contact patterns recover. If they're really scared about a flu, maybe about getting the flu, they tend to be more careful about their hygiene, more careful about who they're contacting. But then as the perceived risk goes down, their behavior changes again. So we can capture that using this bottom formulation. Okay? I didn't have time, I don't think, to cover this online. I have slides I've posted on this. You can find these two formulations, but I want to cover it in person. Any questions on those? Okay, so we have just 1 or 2 minutes here, I think. We're just about over. Just riddle me one question. So we have these first order delays. They're little building blocks. Whether we formulate them in this bottom way or this top way, they're little building blocks that if we build models. But for the first type of formulation, the one on the top, how do we build a higher order delay out of them? How do we build up a series of these things, say to capture people of different ages, where you have the youngest age group, and then the middle age group, and then the oldest age group? How would you do that? Well, the youngest age group could be X, and then we have a Y, which X flows into via the outflow of X is into Y, which is So maybe X is 0 to 4 years of age. There'd be a Y to the right of it, which would be 5 to 9 years of age. There'd be another one older, 10 to 14 years of age, and you'd have successive stocks. Yes. Another stock. I'm sorry. Yes. Yeah. It's another stock. Instead of the cloud here, you'd have a stock, and then you'd have another stock. You just take these pieces and you'd string them together, one after the other. And the good thing is, ladies and gentlemen, if you understand the mathematics of this, you can basically understand the mathematics of those higher order delays. It just extends from this. It's sort of a composition of that. And that was played out, I think, in the most recent video. So you build up these pieces out of individual pieces, which are like first order delays, but they together can capture like the aging of a population into successive age categories, or cars of different lengths of age, maybe cars with poor emissions and cars with decent emissions, cars with excellent emissions on the road. And there's turnover in terms of those stock of cars. So with higher order delays, we're stringing together these sets of first order delays. And if we want to build a demographic model, or a model of demographics of cars or other structures, of buildings of different age, we can do this by stringing these together. And then sometimes we have other exits from them that represent competing risks, represent other things that can happen, like a car is taken out of service, or a person dies, or leaves the population through immigration. So those are some reviews of some elements of first order delays. Those are some two different ways to write first order delays. We've reviewed the equilibrium behavior. We've seen how it runs over time, and we've shown you a little bit more the interface here. Next time, we're going to go into the critical step, the step that really necessitates simulation, and look at nonlinear models. And that's when things get really interesting in terms of the behavior elicited, tipping points, basins of attraction, and you can get different equilibria. And we'll be seeing some practical ways in which this can play out in understanding processes of contagion. Okay? And that material and this material today will be useful in understanding agent-based models, which are going to be a topic we get to in another 2 or 3 lectures. Okay, so that's all for today. Thank you very much for your attention. And I think I will ask you to view a video for Thursday. I'll confirm whether or not that's the case tonight. Okay? Posting the problem set tonight. See if you could take a look at it.